Hi, just one more set of examples from 11.2. We have lots of nice results about random variables and summing them now. And I'll show you a few more of them, but there's many more you could prove now. That there's a sheet I think you might not have downloaded, but just the relationship between all these random variables. And when you start summing them, this is actually a very intense computation. You can get very interesting results. So actually moment generating functions is very helpful for us to see what should be happening when sometimes these things like by hand are almost, well, I wouldn't say impossible to do, but very time consuming. The next very nice result is that the sum of independent Poissons is Poisson, which kind of makes sense. I mean, if you expect so many errors per page in one book and so many errors per page in another book, if you put the two books together, you would expect the sum of the amount of errors per those two books. So I don't think that's it's a surprising result, but we have to show that it's true. And if just to do it outright is quite hard, but using moment generating functions is nice. So how do I do this? So I don't know. I'll do it for, I guess I'll just do it for general n random variables. So let x1, x2, x3, xn be my independent Poisson random variables. And so let's look at the moment generating function of their sum. So this is just exactly what we did with the normal. So this is the product of their moment generating functions. N of t, this should be x2. So now I have to remember the moment generating function for a Poisson, which of course I must admit I do not memorize everybody's moment generating function. This is e to the lambda e to the t minus 1. So this is e to the lambda 1 e to the t minus 1. I'll let lambda 1 be the parameter for x1, lambda 2 for x3, lambda n. Okay, so this is times e to the lambda 2 e to the t minus 1 times e to the lambda n e to the t minus 1. Product of a bunch of exponentials is exponential. I sum their exponents, so lambda 1 e to the t minus 1 plus lambda 2 e to the t minus 1 plus lambda n e to the t minus 1. This is equal to e to the, I can pull out all the lambdas, lambda 1 plus lambda 2 plus lambda n times e to the t minus 1. And this is the moment generating function of a Poisson, where this is the new parameter. So x1 plus x2 plus xn is Poisson with parameter lambda 1 plus lambda 2 plus lambda n. That's a very nice result. And so, for example, suppose that, and here's an application of what I'm saying in case this, like why would this come into play? Suppose x and y are independent Poissons. They both have a mean of 2. What's the probability the sum of them is bigger than or equal to 3? So here's just an application. Let x be the number of calls Dr. Grimaldi gets in a day. Let's say that number is Poisson 2, and y is number of calls I get in a day. Let's say that's Poisson 2. What's the probability on a random day that together we get more than 3 calls, where I expect him to get 2 calls per day, you expect me to get 2 calls per day. So on average, actually, if you add the number of calls we have together, that should be Poisson with a lambda of 4, right? Together, if he gets 2 per day and I get 2 per day, then together we should get 4 per day. So what's the probability then that a Poisson is greater than or equal to 3 when we see actually on average we should be getting 4? So I'm just going to sum a Poisson. Poisson is discrete, so this is e to the negative 4 times 4 to the x over x factorial. I probably shouldn't have used x. That's not really good, right? let's call this new random variable W. Well, so probably W is bigger than or equal to 3. That would make this W, that would make this W. And W, I'm going to sum from 3 to infinity. Okay, nice. Another nice result, sum of independent and identically distributed binomials with the same probability P is binomial. Sum of binomials is binomial as long as you have the same parameters. So let X be the number of free throws I make out of 10, and let's say I have a 70% chance of making a free throw. Let Y be the number of free throws that Dr. Yatesai makes out of 20, and let's say she's also a 70% free throw shooter. Together, if you, let me see, if I'm 70%, you expect me to make 7. If she's 70% and she shoots 20, you expect her to make 14. So together, the number of shots we make together should be binomial with, let's see, together we're shooting 30 shots, but our probability of success is 0.7. So what's the probability combined we make, what's the probability that combined we make at least 25 shots? So what's the probability combined we make at least, so 25 or more shots? You would expect us, actually, if we shoot 30 shots together with 70%, we should make at least 21. So I'm just going to sum, let's call again this W. Let's sum W from 25 to 30. Let me see, this is 30 choose W, 0.7 to the W, 0.3 to the 30 minus W, and just sum that, maple something. Okay, and there's lots of other nice facts. I just gave you some. Sum of independent geometrics is negative binomial. This is the number of trials till the first success, and this is the number of trials to the rth success. So if you sum geometrics, it's not surprising you get negative binomial. Sum of negative binomials is negative binomial. Sum of independent exponentials is gamma. Sum of independent gammas is gamma. So we haven't discussed the gamma, but there's not, I mean, and people come up with these through looking at their moment generating functions. And the sum of a large enough, if you sum a large enough number of any independent random variables, you're going to get back to a bell-shaped curve. And I have some really nice videos showing that. I think I'll save it for the next video because I'm still waiting this exponential one. I've been having it run for about an hour or two now to find the sum of 10 exponentials. This is, like I said, this is not easy stuff. So I think it's only summed 5 of them so far. So when I go to the convention tonight, I'm going to let the sum the rest of them. So by the time I get back, hopefully you can see the sum of exponentials is normal. I'm doing this, running it right now in Maple, and it probably needs to run the rest of the night before I'm done. So I'll show you that in the next video. It's just a nice little thing. And then if you want any more examples on this, I do have this in homework set 7. I've a couple places where I summed random variables, but if you need any more help or you want to see another example, just let me know. And I will post the other stuff later once I convert. Hi, I'm in San Diego, and I'm making a video for 11.2, and I think Jeffrey, right, is in well, he's in California. Who else is in California? I'm not sure. So yeah, we could add office hours here. But anyway, I'll be here all week for a conference, so I'll try to keep up the best I can with homework problems and stuff. I'll be able to at least I'll be able to text, no, not text, but email you back from my phone if you write during the day, and then at night I can probably have more time to answer things. Let me see. So to me, this is the big reason why we have moment generating functions. I mean, why we use them. It's a nice way of finding sums of random variables, and we do this through moment generating functions, so everything happens very nicely. So this is the property I'm going to use. If x and y are independent random variables, then the moment generating function of their sum is the product of their moment generating functions. And so you might think, oh, what does this do for you? But when you find this product, then sometimes it's the moment generating function of an already defined random variable, because remember we have that list of all the common moment generating functions. Maybe you can go backwards and then find out by using the moment generating function what random variable that represents. So it's that nice two-way. I mean, the recognition doesn't mean a lot in that last section, but now when we put two together, it's nice to go backwards and say, oh, that must be the moment generating function of an exponential or a normal or whatever. I think through a few problems I can show you what I mean, and here is the proof of that. So the theorem, if you have n random variables that are independent, we have to have independence, then the moment generating, with these are the moment generating functions of each of those random variables. Then the moment generating function of the sum is equal to the product of the moment generating function. So the proof of this, we need an important fact back from section 8.2, the expected value of g of x times h of x, where these are functions of random variables. So maybe this is something like expected value of x squared times y cubed. If x and y are independent, this would be the expected value of x squared times the expected value of y cubed. And that's what independence can do for us. So I'm going to use this fact in this proof. So this is a nice proof. I mean, when I did it in class, and even when I do it in general during the quarter, people are like, well, what did you do? It's really just using definition to manipulate it and get back to what we want. So the moment generating function, here's a sum of a bunch of random variables, t. So by definition, this is the expected value of e to the x1 plus x2 plus xn times t, which is the expected value of e to the x1t times e to the x2t times e to the x3t plus, times e to the xnt. Now I'm going to use that property. Since x1, x2, x3 up to xn are independent, I can rewrite this as a product of expected value of e to the x1t times e to the x2t times e to the xnt. But this is just the definition of expected value of x1. So this is, this is the definition of the moment generating function of x1. So this is mx1 of t times mx2 of t all the way times mxn of t. So the moment generating function of the sum is the product of the moment generating functions. And then hopefully when we put this together, then we see, because every random variable has a unique moment generating function, maybe we see this as a unique one, and we can go backwards and say what random variable that is. So, for example 1, let's see. Yes, I want to show that two normals. We use this all the time in statistics. If x is a normal random variable and y is a normal random variable, here's its mean, standard deviation. Here's its mean, standard deviation. That if I sum those two random variables, I still get a normal random variable. And I think we kind of take this for granted. You know, in statistics we do it so often. If you sum two normals, you get a normal. And I'm not talking about a mixture. I'm talking about you sum a bell and a bell, you get a new total bell. I'm not mixing them. I'm actually adding two normals to get a normal. So let's show how to do this. So let's look at the moment generating function, and these I should say, oh, very nicely, they're independent. So this is oh, how do I erase this? All right, I have a nice eraser somewhere here. think I just lasso, right? And then just delete it. Okay, so let's go back. The moment generating function of the sum. So m of x1 plus x2 of t. I'm going to see if this is unique or something I know. So I know this is just the product of the moment generating functions. Sorry, I actually used x and y, because this is x and y. So x and y. Well, what's the moment generating function of a normal with a mean of this, a standard deviation of this? So I have my chart here. Let's go down to a normal. I don't see it on that page. Okay, there's a normal, and there's its moment generating function. Okay, so let's go back a minute. So this is e to the mu xt times, let's look at that again, half t squared sigma squared. So half sigma x squared times t squared. Okay, and let's see, moment generating function for y is e to the mu y t plus 1/2 sigma y squared t squared. So we can combine those. I'm multiplying 2e, so this is e to the mu xt plus mu y t plus 1/2 sigma x squared t squared plus 1/2 sigma y squared t squared. So writing it a little bit more nicely, this is e to the mu x plus mu y t plus 1/2 t squared sigma x squared plus sigma y squared. So we recognize this as the moment generating function for normal, where, let's highlight it here, this is my mean and this is my variance. So what we've just shown then is that when I add two normals, I get a normal, because I get a moment generating function of a normal, with the new mean as the sum of the means and the new standard deviation as the square root of the sum of the variances. So, I mean, here's my new, right? This is my new variance, so standard deviation would be the square root of that guy. So this is very helpful in doing problems. Now I know the sum of two normals is normal. I know what the mean would be. I know what the standard deviation would be. So let's switch to blue. Okay, the weight of a math book is normally distributed with a mean of 5 pounds and a standard deviation of 1 pound. So let's xi. There's a probability that 3 independent copies of these books in your book bag weighs more than 12 pounds. So let xi be the weight of the ith book, and each book is normally distributed with a mean of, let's see, 5 pounds and a standard deviation of 1 pound. So what example 2 is saying to us is if we had 3 of these books in our backpack, then their weight should be normally distributed with a mean of mu1 plus mu2 plus mu3 is 15, and then the standard deviation is the square root of 1 squared plus 1 squared plus 1 squared. So the weight, let's just call this the total weight, W, is normal with mu of 15 and sigma as the square root of 3. And so what was the question? What's the probability these books weigh more than 12 pounds? So what's the probability the total weight is more than 12 pounds? I'm just going to do it like we do at a z-score. That's the probability that a normal 0, 1 is greater than 12 minus 15 divided by square root of 3. So this is the probability that z is bigger than I'm sorry I didn't figure this out beforehand, whatever a negative 3 divided by square root of 3 is, and then I would look up in my z table whatever value this is and estimate the probability. So this goes back to normals and z tables and reading them. I think I'll just stop and then start with a new video in a second, just because this is probably getting long.